In this video, I'm going to be discussing the graphing of quadratic functions and their solutions. So if this is a coordinate plane, and here we have our x-axis, and here we have our y-axis, when we go to graph quadratic functions, the graph that we get is known as a parabola. It has a special name and it has a special look to it. Looks a little bit like a U, in this case inverted U, or a V, and it definitely does have a pointy part known as the vertex. But what we're concerned about today is this, the points where the quadratic function crosses the x-axis. Those guys have a special name. They're called x-intercepts. And I'll label both of these as x-intercepts. And it turns out there's a couple of other names for those guys. We also call them roots and zeros. And really there is another name, but I want to take a moment to explain why there's another name. And also maybe I'll shed some light on why we call these guys zeros. Roots, I hope you could be with me, is that the root of the tree is something that occurs kind of when the tree hits the ground. So the x-intercepts, we, at least for memorization purposes, let's consider the points where the parabola hits the x-axis. Let's consider those like the roots of a tree, and we'll call them roots for that reason. But as far as zeros, let's talk about that. So the reason that these guys are known as zeros is because when we have a quadratic function, I'll write one out, y equals x squared minus 7x minus 18. This is a perfectly good quadratic function. By the way, it's in standard form if you want to know a little extra detail. When we write this out, if I replace this y with a 0, let's go ahead and let's see what that looks like. I'll go ahead and make it 0 equals x squared minus 7x minus 18. Then what happens is, if I can solve this guy for x, the x values that I get will be the x-intercepts. Now, let's not confuse things. This quadratic function right here is not, this is not the graph. This graph right here that you see is a different quadratic function. But this quadratic function still has a graph that has x-intercepts, and we can find them by setting y equal to 0. In other words, look over here. Look at these x-intercepts. These occur when, notice here's y. So just to restate, when you have the points where the graph crosses the x-axis is where y equals 0. Here y equals 1, then 2, then 3, then 4, and negative 1, negative 2, negative 3. At these points, y equals 0. So that's another reason why x-intercepts are known as zeros. And again, we'll go with roots as being, well, that's where trees have roots, is when they hit the ground. So anyways, so if I take a quadratic function and I replace y with 0, if I can solve for these x values, then I should be able to figure out what the x-intercepts of my function are. Now, in this particular case, I can use a technique known as factoring to factor out my quadratic function, and when I do, I end up getting something like this. Now, factoring will be discussed in a different video, but for now, let's say that we could factor this guy. When we do, we get our factors like this, and then we use something called the zero product property to say that if we have something times something and it equals 0, then either this is 0 or this is 0. And if x minus 9 is 0, well, then x could equal 9. And if x plus 2 equals 0, then x might equal negative 2. So for that reason, we get these two solutions to this quadratic function right here, to this quadratic equation. We get these two solutions. X could be 9 or x could be negative 2. Well, Since we found these two solutions by setting y equal to 0, it turns out that we have another name for x-intercepts. We can call them roots, we can call them zeros, and it turns out we can also call them solutions. So, when we have a graph of a quadratic function, and I'll show you another one just so that you can be with me on this. A quadratic function could be anywhere on the x-axis, and still, if we have 2 points that cross the x-axis, we'll call those guys roots, but we can also refer to them as x-intercepts or zeros, and we can also call them solutions. Now it turns out we do have other types of parabolas. They don't always cross the x-axis twice like this. But when they do cross the x-axis twice like this, we do talk about the number of solutions in a special way. We say that in this case we have 2 real roots. Now let's compare that to a situation where we don't have 2 x-axis crossings. So it is entirely possible to have a parabola where you don't have 2 x-axis crossings. Sometimes you could have a parabola where just the vertex just touches the x-axis. And in that case, we describe that situation as having 1 real root. That guy has 1 real root. And of course also that's called 1 x-intercept or 1 0. And if we knew what this quadratic function looked like, if we knew what the equation looked like, we could solve for it, and we would get that x only had 1 value. We could only find 1 solution for x as well. Of course, you could also have a quadratic function that had its vertex on the x-axis, where it opens up as opposed to opening down. And by the way, opening down, I call that frowny face. Opening up, I call that smiley face. And we could have a parabola that opens up or down and still just have 1 real root. Another situation that could occur is we could have something like this. Here's our x-axis. We could easily have a parabola that opens up, but it never touches the x-axis at all. And in that situation, we say there are no real roots. No real roots. Certainly no x-intercepts, and certainly no zeros. And it's also possible to have a parabola that opens down that never touches the x-axis. And again, we would call that situation no real roots. Okay, so I believe that I'm good with all the things that I wanted you to know regarding the graphs of quadratic functions and their solutions. We now know that if a quadratic function crosses the x-axis twice, we say that it has 2 real roots, and we also call those roots zeros and solutions, as well as x-intercepts. And if we only touch the x-axis once, we say 1 real root, and if we never touch the x-axis, then we say we have no real roots.